Hello everyone, I'm Alan Jose Garcia, and this is a presentation of the paper entitled On the Interaction Between Distance Functions and Clustering Criteria in Multi-Objective Clustering. This is a work in collaboration with Professor Julia Hunt for the 2021 Evolutionary Multi-Criterion Optimization Conference. The main objective of this work is to investigate the interaction between the clustering criteria employed in a multi-objective algorithm and the distance functions on which these criteria operate. This with the aim of improving and simplifying the design of these methods. The outline of the presentation is as follows. First, I will present the introduction and background of this work, followed by the description of the two multi-objective clustering approaches. Then I will give details about the experimental setup and results. And finally, I will present the contributions and conclusions of our work. Multi-criterion algorithms for data clustering have gained traction because of their ability to deal with diverse cluster properties. In the figure, we illustrate three cluster types that are commonly studied: compact, elongated, and arbitrarily shaped. This diversity of possible cluster properties has motivated the proposal of various cluster quality measures to mathematically capture the underlying cluster structures. It is important to remember that the success of any cluster quality measure depends on two main aspects: its mathematical definition and the dissimilarity function it operates on. So let's have a look on some dissimilarity functions and their impact when identifying cluster structures. Let's start with the definition of a well-known metric, the Euclidean distance. This metric belongs to a family of distances known as the Minkowski metric. The figure illustrates the behavior of three Minkowski metrics when measuring the distance between a pair of data points. The use of these distance functions when identifying cluster structures tends to result in spherical groups. Now let's consider a less well-known distance function. The met distance is defined over a minimum spanning tree of the complete graph, which represents the original pairwise dissimilarities in a given dataset. So it implicitly operates on a second distance function, which could correspond to the Euclidean distance. This measure redefines the dissimilarity as the longest edge encountered when traversing the MST between two data points. In order to better understand the differences between these two measures, let's consider their impact on some simple two-dimensional datasets. The figure shows four datasets that exhibit a range of different shapes. This original visualization reflects the actual coordinates of all data points. We can then apply our different dissimilarity functions on these datasets. Here, we use the Euclidean distance and the maximum edge distance. Once a dissimilarity matrix for a dataset has been obtained, we then use multidimensional scaling to re-embed the data into two dimensions. It's evident from the results in the figure that the choice of distance functions makes a fundamental difference to the identification of particular clusters in the embedding obtained. Specifically, the met distance favors the clear spatial distinction of arbitrarily shaped clusters, for instance, the spirals dataset, but is less capable than the Euclidean distance in separating clusters with overlap, for instance, on the size 5 dataset. Given the definition of these two distance measures, this observation is perhaps unsurprising. Nevertheless, it has led to the question of whether improved clustering performance may be achieved from a combination of these two measures. Furthermore, it also raises questions about the interaction of these distances with clustering criteria and the extent to which the limitation of a specific clustering criterion could be counterbalanced through the choice of a distance function. This paper, in this paper, we focus on this question in the context of multi-objective approaches to data clustering. The figure shows the main stages of the multi-objective clustering approaches that we are investigating. algorithms for multi-criterion clustering on the top, and algorithms for multi-view clustering at the bottom. Here, we use the term multi-criterion clustering to refer to the optimization of several complementary cluster quality criteria. For example, the cluster analysis task could be formulated as a multi-criterion optimization problem that simultaneously minimizes the intra-cluster homogeneity and maximizes the between-cluster separation. Generally, compared to single criterion approaches, the multi-criteria algorithms have demonstrated their robustness when identifying different clusters properties. However, the model selection stage poses some additional challenges. On the other hand, the emphasis in multi-view clustering lies in integrating multiple feature sets or multiple dissimilarity spaces rather than the integration of multiple clustering objectives. In an unsupervised multi-view learning problem or multi-view clustering problem like this one, given a dataset in terms of a single feature space, multiple distance functions can be considered and integrated when attempting to improve the robustness of the final clustering solution. In the following, we briefly review two specific evolutionary algorithms for multi-criterion and multi-view clustering that after we use to underpin the experiments and analysis in our paper. DeltaMock is a multi-criteria clustering algorithm. It uses the NSGA2 algorithm as the underlying optimizer. It uses a flexible representation which avoids the emphasis on spherical clusters typically associated with a prototype-based encoding, makes no prior assumptions on the number of clusters. It formulates the multi-criterion clustering as a objective problem. Let's focus on the two objectives considered by DeltaMock. The criterion of within cluster sum of squares assesses the compactness of a partition, where D is a distance function. Typically, this is Euclidean distance, but other choices are possible. In contrast, the criterion of connectivity is more complex and caters towards the density preservation of the dataset. The two objectives are known to have opposite trends with regards to the number of clusters, allowing DeltaMock to efficiently explore a range of possible cluster numbers. DeltaMock uses a complex linkage-based representation that allows it to fully explore trade-offs between its two objectives. Regarding the multi-view clustering approach, we consider the MBMC algorithm, which was developed to identify optimal trade-offs between data views. It uses a decomposition-based optimizer as the underlying search engine. It achieves scalability to a number of views through the use of a many-objective approach. It uses a method-based representation which is more general than centroids. It requires as input the number of clusters. It focuses on a single clustering criterion but aims to optimize this with respect to every data view. The clustering criteria is defined next. For the computation of its clustering criteria, MBMC takes as input M dissimilarity matrices. Let C and R be the partition and weight vectors corresponding to the R subproblem. The M objective of the subproblem is computed as the within cluster scatter with respect to each of the M data views in the multi-view data problem. So MBMC focus on a single cluster quality measure but aims to optimize this with respect to every view, giving rise to a multi-objective optimization problem. At the face of it, MBMC would appear to be significantly less powerful in the context of arbitrarily shaped clusters, as it assumes a prototype-based representation and a compactness-based criterion. In our paper, we set out to investigate the extent to which this really is the case. A total of 20 datasets are considered in the experiments of this study. This figure illustrates the diversity of cluster structures covered by our benchmark data. This data set express varying sizes, degrees of overlap, and cluster shapes, including complex combinations within the same dataset. The adjusted run index is used to assess clustering performance. This index returns a value between 0 and 1, such that the larger the value, the better the correspondence between the partition obtained and the true partition of the data. Each run of MBMC and DeltaMock produces a set of candidate partitions. From this set, the best solutions in terms of ARI is reported in the results section. We compare MBMC and DeltaMock to each other and also against two well-known and conceptually different single objective algorithms, k-means and single link. Two MBMC configurations are considered: WGS, which minimizes the within cluster scatter, and SIL, which directly optimizes the silhouette width. Please visit the manuscript for more details about the parameter settings and significance test. The table summarizes empirical results of our experiments. It shows the clustering performance in terms of the ARI index obtained by the reference clustering algorithms on the test datasets. From the table, we can observe that comparable results to DeltaMock can be achieved by using MBMC with two complementary distance functions. MBMC's competitive performance with respect to DeltaMock is perhaps surprising given that MBMC optimizes a compactness-based clustering criterion. It is clear from these results that the simultaneous use of the Euclidean and Met distance helps to exploit the structural information in the data to the same extent than the use of multiple clustering criteria. A remaining limitation is that MBMC currently does not explore multiple number of clusters, but this is something we hope to address in future work. To understand our results in more detail, it's interesting to also look at the approximation frames obtained. This slide shows empirical attained functions computed from the Pareto front approximations obtained by MBMC and DeltaMock. We can highlight that these Pareto fronts can be compared directly because the ones on the right shows the trade-offs across a range of a number of clusters. In contrast, the ones on the left are trade-offs of a single case when the cluster number is fixed. For MBMC datasets that are fairly trivial with well-separated clusters, there is essentially no conflict between the criteria. However, as we introduce more complexity in the datasets, we can observe a trade-off, and the best solution tends to be located in the middle of the Pareto front. Also, for the arbitrarily shaped clusters, the best solution tends to be in one extreme of the Pareto front. For both algorithms, we can confirm that the location of the best solution found in the Pareto front moves around depending on the complexity of the input dataset, justifying the use of a multi-objective approach. Finally, our paper includes a mathematical analysis of the formulation of DeltaMock's objectives in order to understand the similarities in differences between DeltaMock and MBMC and how this leads to the performance observed previously. The similarity in the first objective is straightforward as both algorithms optimize a compactness-based criterion. However, DeltaMock's second objective looks very different and it's known to account for DeltaMock's ability to detect complex cluster structures. We observe that the objective can be reformulated as a minimization problem over a non-parametric dissimilarity measure. Basically, this definition indicates that DeltaMock's density objective can be rewritten as a compactness-based criterion formulated over a more complex distance function. This formulation highlights the similarities to MBMC's second objective, which also computes a compactness-based criterion, the within cluster scatter over the mid-distance. Please refer to the manuscript for further details about this mathematical analysis. Our work makes the following main contributions. For delta Mach, mathematically, the underlying multi-criterion optimization problem remains equivalent, but the reformulation explicitly highlights the parallel to a multi-view approach, resulting in a transfer of algorithmic complexity from the criterion to the distance level. For MBMC, empirically, competitive results to multi-criterion clustering can be obtained when a multi-view algorithm is used with a suitable pair of distance measures. In general, we show that the suitable choice of a distance function can overcome the common limitations of prototype-based encodings and compactness-based criteria because it allows the design of algorithms that can cater to a broader range of cluster structure and because it transforms the input data into a simpler space. That's all. Thank you all for following this presentation, and I'm looking forward to your questions.